Step number 2, capacitor bank size and resonant frequency computation. In general, the filter size depends on the load reactive power requirement for power factor correction. If a power factor correction capacitor is already installed in the system, it is converted to harmonic filter just by adding inductance. In such case, the capacitor size is known and the reactor size will be determined to tune the capacitor at the desired frequency. For example, in this particular example, there is no power factor correction capacitor installed. Moreover, the desired power factor is 0.96. The capacitor rating and the capacitive reactance can be determined by using the following. So we know the current power factor of 0.79. We know the size of the load, which is S. Then we know that S cosine will be equal to P, right? And then to find Q, to find the current Q, so it will be P tan the angle, which is cosine inverse. So that will give us Q. So as a result, now we're able to create the power triangle. Okay, we calculated P, we calculated Q, and of course this angle is also given to us, which is cosine inverse of 0.79. Okay, now when we like to improve the power factor to 0.96, then we can calculate what will be the reactive power demand in this case. Okay, so now we know that we like to improve the power factor. So again, this is P, this is the first for the initial reactive power, this is theta 1, right? And now we like to improve the power factor, as he told us, to a smaller angle. Therefore now we can calculate also what will be Q2, right? And the difference between Q1 and Q2, that will give us the Q for the filter. Okay, and we should not forget that the filter consists of both capacitor and inductor. So the difference between Q1, which is calculated from step 1, and Q2, which is calculated from here, will be the required size of the filter. So the filter will supposed to provide to us 460 kilovolt ampere reactive. So once we know Q, we can determine XF. We can find the reactance of the filter, V square over Q. That will give us the reactance of the filter, right? And this reactance, of course, we should not forget that it consists of not only capacitor, but it contains both capacitor and inductor, because it is a filter. And now he told us, of course, in the problem that we need to get rid of the fifth harmonic. So over here we have to tune it below the fifth. Let's say that it is tuned at 4.7. Okay, so then now we can calculate what will be the value of the capacitive reactance. Okay, so we know the relationship between XC and XL as H, right? So if we able to calculate XC, then we will able to calculate XL, right? We know also from the previous chapter that the reactance of the capacitance with respect to the reactance of the filter can be obtained from this equation. So the capacitive reactance will be equal to the reactance of the filter times the tuned times the harmonic factor over a square over the harmonic factor square minus 1. So that will give us the value of the capacitive reactance, and then of course we can calculate the reactance of the inductance. Okay. Therefore, to achieve this, then the capacitor has to be rated at the following. Okay, because don't forget that what we have calculated is Q for the filter, right? By subtracting the initial Q minus the new Q, that gives us the reactive power of the filter. But now we have to calculate the reactive power of the capacitor bank. So we know the voltage, we know the inductive reactance. Then we can calculate what will be the reactive power that's supposed to be provided by the capacitor bank, and it is found to be 438 kilovolt ampere. Okay. The commonly available capacitor rating close to the calculated one will be 450 kilovolt ampere. Okay, reactive. Because if we go to the market and we like to buy such kind of capacitor size, it will not be available maybe with this value 438. So we have to choose the one which is available in the market, and that one should be very close to 438. So that's why we choose 450 kilovolt ampere reactive. So now we're gonna select this size of capacitor 450. Then we can now recalculate the value of X again, right? XC, because we know that XC will be equal to V squared divided by QC, and now the new QC is 450 kilovolt ampere reactive, and that will give us this value of XC, right, based on this Q of the capacitor, which is available in the market. So this one will be XC if the capacitor bank is connected in Y. But if we like to make a connection in delta, of course, yes, we need to multiply it by 3. And also now we can calculate what will be the rated current of this selected capacitor bank. Can calculate the current from the rated of the capacitor bank and from the voltage of the capacitor bank. So that gives us the rated current, which is 441. Okay, and now again we can also recalculate the value of the inductance, because we should not forget that we selected capacitor bank from the market, and we find it to be 450. So that gives us different XC. So now we need to calculate the new value of XL, and again the new value of XL can be calculated from this equation. So that will be 0.023 ohm, and then we can calculate L. Okay, so this is how can we design or select the value of the inductance. Step number 4, we have to check the filter duty requirement evaluation. So we have to evaluate the filter requirement, which are, we should not forget, the root mean square voltage, the root mean square current, the kilovar, and the peak voltage. So those 4 elements that need to be checked according to the standard, according to IEEE standard 18202. So we're gonna check the fundamental duties, the harmonic duties, the peak voltage, and root square. Okay. The filter draw more fundamental current than the capacitor. Okay, so don't forget that we have a filter that consists of a capacitor and inductor. Okay, the actual reactive power produced. So from our initial calculation, this was the Q of the filter, and this was Q for the capacitor bank. This is according to our initial calculation. But then we said that we're gonna select a new capacitor because this is not available in the market. We're not able to obtain 438.4 kilovolt ampere, right? Reactive. Okay, so we have selected this size of capacitor bank for 150 kilowatt. As a result, also the reactive power of the filter will change. Initially it was 493, and now it will change because we change the value of the because we change the size of the capacitor bank. So the new size minus the old size, so then this one will be the new kilovolt ampere reactive for the filter. Okay, and we can calculate the current that passes through the filter from the Q and from the voltage. So that will give us this value of current. Okay, for again for this size of the filter. Step number 6, we have to check the harmonic duty requirement. Okay, so let's say that this step is dedicated to compute the maximum harmonic current in the filter. Okay, so we have in filter we have the fundamental current through the filter. We have the harmonic current flow through the filter. So from the nonlinear load, this is one side. Nonlinear load is providing harmonic current, and also we should not forget also the voltage level. The voltage level will have also harmonic 1%. So we have to consider both. Okay, we have fundamental current flow through a filter that passes through a filter. We have harmonic that coming from the load, and we have harmonic that come from the voltage source as well. The harmonic current produced by the non-linear load that was assumed to be 25% of the fundamental current. Okay, so we know the fundamental current will be the S divided by root 3 divided by the voltage. Multiply that one by 25%, so that will give you the fifth harmonic current. Okay, and again we need also to calculate the harmonic current that comes from the utility, because the utility, it has also harmonic. Okay, he told us that it has 1% of the fundamental voltage. So the fifth harmonic voltage was given according to the problem or to the example 1% of the fundamental voltage. Okay, we need to consider that one, and that of course is coming from the transformer. Okay, so that is coming from the transformer. So we need to calculate the impedance of the transformer. So we know how to do that. V square over S times the transformer impedance in per unit. So that will give us the impedance of the transformer. Okay, and also we can calculate the impedance of the capacitor bank for the fifth harmonic. Okay, so that will be the value. We can calculate also the impedance of the reactor for the fifth harmonic, and that will be the value, okay? And also we can calculate the impedance of the transformer with respect to the fifth harmonic, and that will be the value, okay? So we should not forget that we have transformer, okay, and then over here we have the filter, like that. So over here what we said that fifth harmonic of the voltage times the fundamental, okay? So that fifth harmonic voltage will create also a current, right? So that current will flow through the transformer, will flow through the capacitor, will flow through the inductor, okay? And that we call it the harmonic current that come from the source, okay, which is written over here, okay? So we have the fifth harmonic voltage will be equal to 0.1 times the fundamental voltage. Then we have to divide that one by the impedance of the transformer, the impedance of the capacitor bank, the impedance of the reactor, okay, and that will give us 46.5. So now we have harmonic current that comes from the utility, we have harmonic current that comes from the non-linear load, okay? So then the total harmonic current will be the summation of both, and that will be 407. Okay, also we can calculate the harmonic voltage across the capacitor, okay, because again we like to check the duty of the capacitor. So then the fifth harmonic voltage that will be applied across the capacitor will be given by the reactance of the capacitor for the fifth harmonic multiplied by the total harmonic current, the fifth total harmonic current, of course time root 3 because this is the line voltage. So that will be 72.2. So that will be the harmonic voltage across the capacitor. And now step number 7, we calculate the total root mean square current and the peak voltage again for the capacitor bank, because we like to verify that the capacitor bank is fulfilling the IEEE standard, okay? So then how can we calculate the total root mean square current? We have to calculate the fundamental current and the harmonic. So the fundamental current is already calculated previously, and the harmonic current is just calculated in step number 6, and that will be 698. Okay, we can also calculate what will be the maximum voltage across the capacitor. So we have the fundamental voltage and we have the harmonic voltage, right? So those will be added, the fundamental and the harmonic voltage. We can also calculate what will be the root mean square value for the voltage across the capacitor, line to line. So again we take the fundamental and the harmonic. So that will be 508. We can calculate now what will be the kilovar of the capacitor. So it will be voltage root mean square, current root mean square times 43, and that will be 640 kilovar. Now we can compare between the standard as specified by IEEE and what we obtain from this problem. Okay, so with regard to peak voltage, we are in line with the standard. With regard to root mean square voltage, we are in line also. With regard to the root mean square current, we are in line. We are less than what is given in the standard. And with regard to kilovar, also we are in line with the standard. We have very close value to the standard, and just 1% difference. So we can say that we are also in line with the standard. Okay. This slide shows that the proposed filter duty requirements are very close to the limit. So as we said that. Therefore, there is no tolerance for any deviation in the assumption or increase in surface voltage. In such a case, 480 capacitor will have a short life, right? Because it has, again, there is no tolerance. The value is very close to the standard, right? And even this value is exceed 1% from the standard, but those are very close. So any tolerance in the capacitor bank that will exceed the standard, right? Any deviation in the value of XL, XC that may increase this value, then it will be beyond the standard. So that's why we said that there is no tolerance for any deviation in the assumption or increase in the surface voltage. As a result, the capacitor bank will have short life. However, let us assume that the capacitor that we choose will be working at 600 volt. Then in that case, what will be the new reactive power that will be provided by the capacitor bank? Will be 703 kilowatt. A normal capacitor rating of 700 var with the reactor value as committed in step 3 would provide the same filtering action within the normal manufacturing tolerance. So now what we are saying that we're gonna choose a capacitor that will have a higher rating, since we choose a capacitor that will work or that will handle a voltage up to 600 volt. Okay, step number 9, filter reactor design evaluation. So this step is dedicated to evaluate the reactor parameter. So this is the value of XL as calculated before. Then we can find the value of the inductance, and also let us assume that the quality factor will be given as 50. So from there we can calculate what will be the value of the resistance. Okay, so the value of the resistance will be 0.0022 ohm. Filter frequency response evaluation. This step is dedicated to evaluate the filter frequency response to ensure that the filter does not create any new resonance at the frequency that may cause additional problems. So now we need to check how the impedance of the filter change with the frequency. Okay, so we should not forget that once we place a filter that consists of a coil and capacitor bank, which is connected with the system. So over here actually we have a transformer. We could have also a system impedance. Then this one will be our harmonic equivalent circuit. So as a result we have also parallel resonance, right? So we say that the harmonic at which the parallel resonance below the notch frequency will occur can be expressed by assuming that the surface transformer reacts to dominate the source impedance. Okay, so we can find the harmonic order for the parallel resonance. We have XC and divided by the summation of both the XL and X for the transformer. So that will give us harmonic order of 3.97. This reveals that the filter result in a resonance close to fourth harmonic. And of course this is fine since the harmonic current that will be generated from nonlinear load that will not have the fourth harmonic, will have only the fifth. So we are fine. Normally a very few harmonic source generate even harmonic during steady state operation. Consequently the design filter will operate very properly. However, fourth harmonic current can occur during transient operations such as transformer energization. Such a case, filter design have to consider utility resistance impedance in their calculation, and the basic filter size would have to be increased to gain additional margin from the fourth harmonic. Step number 11, evaluation of the effect of filter parameter variation with unspecified tolerance. While designing a filter, designer should usually consider the following tolerance: 15% plus tolerance of the nominal capacitance value, minus or plus 5% tolerance of the nominal corrector inductor. Such tolerance can significantly affect the filter performance and can create a harmful resonance. Therefore, the final stage in designing a filter is dedicated to check the filter design for various extremes. This is automatically done in some filter design software.